that's released when the electron falls, okay? And I know some of this stuff is probably very obvious to you guys, but when an electron falls, it releases energy. And it releases energy in the form of light. So light will come out. Now how do I find that wavelength of light? Well, you know the energy, right? And you know this equation. Okay? Now, what's my energy in? Kilojoules per mole. Planck's constant. I've always reported Planck's constant two ways. 6.626 times 10 to the negative 34th joules per second per one particle. Or I've always just gone ahead and calculated the per mole part. You could have it as 3.99 times 10 to the negative 13th kilojoules per mole, or kilojoules second per mole. So if your energy is in kilojoules per mole, use the 3.99 times 10 to the negative 13th kilojoules times seconds per mole. I don't see this ever reported anywhere. I just calculated it because it's used so often. That way you're not, because how do you convert from this one to this one? Divide by 1,000 to convert it to kilojoules, and then multiply it by Avogadro's, or multiply it by Avogadro's. Okay, but sometimes it's just easier to have that written somewhere. So what happens when an electron jumps to a higher energy level? Is it energy absorbed or released?
Absorbed.
Or absorbed, right? So you can shoot light in to cause it to jump to a higher level. It must have exactly the right amount of energy to jump. If it doesn't have enough energy, it can't jump to the next level. Periodic trends. As you go down, radius gets bigger. As you go across the periodic table, they get smaller. So really, like an explanation, potassium versus cesium. Cesium's in the 6th energy level, potassium's in the 4th, cesium is going to be the bigger atom. If I compare cesium versus bismuth, they're both in the 6th energy level. But as you go across, the nucleus pulls the electrons in slightly. So every time you go one over on the row, you add one proton, you also add one electron, but that proton has the effect of slightly shrinking the atom. So cesium will be slightly bigger than bismuth, because bismuth has more protons, it'll shrink it. But dropping down a level has a huge effect, okay? So that's atomic radius. For the other trends, like ionization energy and electron affinity, you need to look at electron configuration first. So, like, they always like to ask exceptions. So, if you look at, as you go to the corner, ionization energy increases, as well as electron affinity. That's the trend. But they like to throw, like, exceptions to the trend at you. So explain why, or they might actually predict first, why does beryllium have a higher ionization energy than boron? Because here's beryllium, here's boron. So boron should have a higher ionization energy. But it doesn't. Beryllium's got a higher ionization energy. And with these two trends, the first thing you do want to look at is electron configuration. So if you don't remember how to do the orbital filling, you really should. beryllium is helium 2s2. Boron is helium 2s2, 2p1. So the first thing you want is a completely full energy level. So something like neon, neon is helium with a 2s2, 2p6. Second energy level is completely full. So it's got a really high ionization energy because everybody's paired up, everything's stable, it's good. It's not going to want to lose an electron. If you can't have a full energy level, go for a full sublevel. So having just the S level filled is going to be stable. So, 1 second. Hello.